All right, this is one of the videos I'm making that goes along with, I guess I'll call it a class on project finance theory and contracts. Now, in this class, the exciting thing really is working through some famous case studies if you're young, and unfortunately I think a lot of people haven't even taken a project finance class and haven't gone through some of the real history, but much more importantly, perhaps you're at a disadvantage if you have taken a class, because I've seen people trying to work betas and even Modigliani and Miller ideas into project finance. The essence of project finance is so much more than debt, so much more than just changing a capital structure around its valuation. It's a way to value, it's a way to come up with low cost of capital. So I go through some studies there, and then to really illustrate things. Now, I'm a total non-believer in practical applications of Monte Carlo. I think maybe there are some, of course there are some, but to illustrate concepts, Monte Carlo can be beautiful. And the first kind of, so as we go through the slides, and I'm making a video about this, I'm going to also make a video about how you can do simulation and demonstrate how mean reversion and volatility affect the DSCR that's required, and affect really how you use those to measure risk. And then I've got a file that does some kind of basic, whatever, IRRs, and another one, and some commodity prices for a case study and double case, which I love, but I'm not sure that's worthy of a video. And then this one, we're going to do a little bit of a solar case study. And to understand solar, I'm trying to promote the idea to not be afraid to really work through how you compute, how you can gather data, how you can get all the way to the bottom. It's kind of the opposite of AI and ChatGPT, the polar opposite. Go get the hour by hour data for many years. Take that hour by hour data, spend a few minutes analyzing that data, and then put some temperature coefficients, compute the performance ratio yourself. That's what I'm going to do. And then we're going to have some other files that work through the debt concepts. I've done a lot of that already, but I might review it. And I'm going to try, I hope this works, we're going to have a little case study where I can't do that on a video, but maybe we can pretend a little bit on you take a role, the investor, you have to negotiate with the lender, you have to negotiate and come up with a resource analysis, you have to make an EPC contract, so I'm trying that. Okay, so this is just one of the videos, and this video, and there'll be other videos that kind of work through this. I'm starting with some of the detailed videos and then going further. And of course, I think project finance is an absolutely crucial subject because you can use it to reduce the cost of capital on non-fuel intensive, non-carbon producing investments that are so much more important than all of the getting the cost of capital for these investments is so much more important than getting the cost of capital down for a gas plant, an oil plant, a coal plant, whatever, a refinery. Okay? Okay, this is a video about using PVGIS. I go to Google and I don't get this one. I don't know what it is, but I go to this one. which has the EU in URL. Now, here's my thought, and it's a general philosophical idea. Let's say you're being a banker for solar. You're not some technical engineer for solar. You're just a banker, not just a banker. It's really, really important, of course. And Mr. R.A. Fisher, who's long dead and is canceled now, he came up with the F distribution. He was totally the father of statistics. He refused to do any kind of analysis unless he understood exactly where the data come, all the way from the bottom. It's kind of the polar opposite to ChatGPT, I think. Not that I'm certainly an expert on that. So what I'm going to show you is how we can evaluate, come up with P50, P90s for solar in different areas, really understand what's going on with solar, understand the effect of different modeling of solar power. So we're going to go to this website. Again, if you're one of these people who criticizes Germany and France and all that, you know, what they did in this thing is really kind of amazing. Now, in this case, I'm going to compare Copenhagen and Saudi Arabia. And I'm going to evaluate and see if we can't come up with some understanding of where numbers come from. We're going to put our own temperature coefficient in. We're going to put a DC to AC to DC ratio in for the inverters. We're going to put in some line losses and recompute hour by hour by hour the performance ratio, just so you can understand where these things come from. Now, let's go. So the first thing, we can go grid connected, but that's just not even tracking. We're going to put tracking in here, and we're going to have to make some assumption about whether these panels are bifacial or not. Okay, and so let's visualize the results. And then we've got some extremely flat kind of production, even though, you know, it is the northern hemisphere, and we kind of get some differences. And then we've got the energy that goes out to the grid for 1 kilowatt of peak. That's with 1,000 STC, how much goes out to the grid. And then we've got the in-plane radiation expressed as kilowatts hours per meter squared, but it almost doesn't matter because the definition of this is 1,000. This is 1,000 is capacity, so this produces at 1,000 watts or 1 kilowatt, and basically they're the same number. This is how much touches the panel on the top, and this is how much you get out at the end, and you divide this by this, and you get the performance ratio. So the thing that it's almost, for me, not worth it to do this, because we get hour by hour data, and in this case, I get this PVGIS Sahara 2, and somebody can explain to me, perhaps, whether this is a better model or not a better model. So we're gonna go ahead and get that time series of data, and then when we get this time series of data, I'm going to match it up, Control A a couple times, and then I'm going to match it up with another file that I don't have open that I've already begun, and that doesn't matter, and it, oops, And this one is called solar resource analysis. And I'm going to compare two areas and show you how you can come up with very effective graphs when you get this stuff on an hour by hour by hour basis. So I've already done a little bit for Copenhagen, and let's put our Saudi thing here. Now, what I'm going to do also is go back and get the, this one. Let's get this thing. Remember that we used this, I've got another case study I'm going to show you about. And we'll put this into our sheet for Saudi first, and then after that, let's put in the excuse me. Let's go, and let's put in our let's put in our visualization. Now, the reason I got this partly is because I want to make absolutely sure if we want to go back and get this exact place again, we can get the latitude and the longitude and just put those in. Okay, I suppose, yeah, why not? Leave it like that. Okay, and let's go back and get that. And the reason I'm getting that is I want to prove to you that when we have this hour by hour data, we're going to get this, and then we're going to see if this total loss, which perhaps is 26%, is that what kind of, if we put in different temperature coefficients, different losses, different perhaps losses even for cleaning the panels, what kind of results will we get? And the other thing, so I want to, but the very first thing to do is really match this. So we'll put this here, and then let's now put the Saudi Sahara okay, and I just had downloaded that, I believe, and that's here, and this would be January of 2005. And I hope you're still with me. I hope you have not turned off this video because it's too completely and utterly boring yet. I promise it won't be. For me, it's really, really exciting. And the exciting thing to do first is to let's put a date in, 1/1/2005. Now, if you press Control 1, you can go to the number and get the hour and the date. And this is absolutely the key. Now, instead of doing that, I would like to do this and make a macro that formats this date much better so we can go down one by one by one by one. And it's kind of interesting. This one actually started with 431, and it's clearly wrong. So the first thing you can do is do your little macro and go to the developer, record a macro, and let's call it Shift Control K, which J, capital J, Shift Control capital J. Now, after you do that, if you want to go and change this, I hope that I didn't just move. I don't think I did. And let's put our little new format in here. Okay, and this I think is really important. So please, if you're saying, you idiot, what are you wasting my time? Then stop recording the macro. Okay, and then you do what you want to do with macros all the time, and this one is macro 2, and you want to change it. And you want to put I would like to see the day first, and then the month with 3 little things, and then maybe 4 Ys, and then the hour. And if I really wanted to get fancy, I'd put D, and then I get the day of the week. Okay, so right now, if you press Shift Control J, it's too wide, but who cares? We're going to kind of go nuts with it. January 1st in 2005 was apparently a Saturday. Now the next problem is these times are Greenwich Mean Time. And we have to think, well, I believe there are 3 hours difference. So I'm going to take this and put -3, but to get 3 hours difference, you divide by 24. You can divide by 48. And this is the brilliant kind of thing. Shift Control J, and then we can start with this, and we can put +1, Shift Control, and now we're here. Now I did a Shift Control H. Let's not put the day of the week. That was kind of overboard with that. So I made another macro, and what I must have, please, if you're doing this, it's manual, okay, and I didn't divide it by 24. I did that on purpose. Okay, and then I should have, instead of, and I always get this wrong, I should have, and now I'm really going bad, yeah. I should have added it, and then we go from 7 in the morning till 5 at night. That's how much sunlight we have, and let's kind of go all the way down to May, and we start at 6 in the morning and go to 6 at night, and I hope I've made the right adjustment to the Greenwich Mean Time, okay? And the whole trick, now we're really finished. We're really just finished, because now we can work with the dates however we want. So let's first get the year. And then I'm going to press Shift Control to the left of the 1 to get the format here. And then I go over here, 2005, and the other thing you absolutely, when you're playing with this data, and it's almost just as fast as going to the website, but you will see just in a minute, you can really see what's happening in a very effective way if you put Alt-EIS and put columns, and we're getting hourly all the way to 2020. And we just get that, and now SUMIF, and remember, I go crazy about this, but this doesn't take any more heaviness or whatever you want to call it. Now the other thing is, look at this, it's got wind speed at 10 meters. How cool is that? We've got some wind speed hour by hour data. Now I'm sure that's not perfect, but we can work and derive what the Weibull distributions is, and we can do things like correlate the wind to the solar for if we want to put batteries eventually, and then, and I just opened generic macros. Okay, and then we have the each hour by hour, and let's put the average. Now we're going to work through, in this video, I'm going to work through just a little bit on, this is, I'm going to call this in plane, and this is kilowatt hours per meter squared. Okay? And if we look at this, 3034. Oh my gosh, 3034, right down there. It's the average. It worked. And just to illustrate now what you can do with some of this, and let's just go ahead and make a graph. Now, I think looking at about a week of data, or maybe even a month of data, might be pretty good. So what I did is I just put a little spinner box on a month, day, and a year, and let's get a date. Okay, and put equal date, and get the year, the month, and the day, and then just Shift Control 3. And we're going to put some performance ratio assumptions in. But perhaps I would like to compare for your birthdays, different years, different days. I would like to compare the in-plane radiation in Saudi with Copenhagen. Now I'm going to, if for a week, there are 7 days in a week, and there are 24 hours in a day. Okay, so we agreed that it was 168, Alt-EIS, columns, you can press Alt-C, but I'm not so good at that, and let's press 168 hours, and oops, excuse me, I don't think you can get COVID on the video. Okay, and then we can put our date here. All right, and when we have this date, the nice thing we can do is, let's start with that date, and then we again add 1 divided by 24, excuse me for that. And I'm going to double click and do our little macro, Shift Control H. And now, when you make this graph, unfortunately, the date kind of function won't work, so it might be good to move this little thing here. I know that because I've tried it. And then we just do a whole bunch of lookups. We go completely crazy with the lookups, and we get first we're 1 January of 12, okay? And that's not going to be a very good one, and this is going to be in plane, and then we can, let's put this here, let's get a Shift Control J, I think, right? Okay, so that's a Sunday we began with, as if the sunlight really makes a difference to what day it is, you know, does it? Maybe you think it does. Look up again, and then we'll look up this one. I switched the sheet, so don't do that, because then it'll put those sheet names in all the time. And let's get the temperature. Now this temperature is the ambient temperature, and they give you the temperature in the nighttime, as if you care about this. And we have to understand the difference in the temperature that hits the panels, which we're going to use in the analysis of our performance ratio. Okay, and unfortunately, you try to find, you look over the internet and you Google and you maybe even go to ChatGPT. Tell me how much hotter it is on a panel typically than it is than it is just for the outside temperature. I was hoping to get some nice little linear equation or something like that. And really, there is nothing. There's a word for it that I can't right remember. Let's press alternate and F1, and let's click X on this one, and put it over here. And we have our, let's put in our chart title. Oh no! Again, put an equal sign, make sure the equal sign goes here, of course. And we have this. So now we can, just temporarily, I think what we'll do is make a lot nicer of a kind of analysis. But this just illustrates the kind of fun you can have when you get hour by hour data. And we really haven't begun. And if this video takes me a little bit long, I don't care, because I'm going to use this same kind of analysis for the I'm going to use the same sort of analysis for the batteries, and even some, I suppose we could even kind of move to some hydrogen analysis and see what if we have surplus solar, what do we do with it? So of course we get our date. And I didn't do what I didn't graph the temperature just now. I'm sorry. Let's get our date. Okay, Shift Control J, why not? And put, I suppose we could do this. Well, there's no reason we couldn't do it like this. Equal lookup. Equal lookup. And we go to, okay, Shift Control H maybe, and let's put an equal sign and add 1 divided by 24. If you're like me, you might forget sometimes to add the 24. And I hope it took me to the right length, you know, of the thing, and then we'll get our solar, and did it go to, it just went to 168, perfect, in plane, and then we put a temperature, okay, equal lookup, this date, and enough. I'm gonna stop doing that. No more of any of this, because it's really so easy. And this time we can see, we get a little hotter. Now I suspect that the temperature on the panels might be a lot warmer than this. So this time let's make a graph of both of these, which is really what I meant to do. And how about we change the series chart type, and for the temperature we'll put a line, and let's put that on the secondary axis. And what you'd expect to see is the correlation. When it gets hotter, the temperature is higher. It's kind of funny that it lags a little bit. And let's get our date. Okay, and let's I'm getting that. Okay. Maybe I'm just getting to... So let's cut this one and put this together, and I don't really have to, I'm going to pause the video because I'm going to put the temperature in on this one, okay? So let's just look at around a little bit. So let's maybe go to June. And in June, we start to see some radiation where it gets to 1,000. This is very interesting. In Saudi, it didn't get up to 1,000. Let's go to July maybe, And then, of course, these are cloudy days. So you see a lot more variation in Copenhagen than you do in Saudi. Okay, and at least we can start, and maybe if we do it a different year, okay, the clouds cover, the clouds are at different years, and we can evaluate it. This is kind of interesting. In this week, we had more solar power, and the temperature got up to 25. For Saudi, and again, this is purely, we get up to 1,000 just in a little bit, and our temperature goes up to 40, but this, if this is in-plane radiation, this in-plane radiation is not affected by the temperature yet. All right, so now let's keep going. So now I've changed around things a little bit, and I've tried to take, instead of this Sahara 2, now I assume the Sahara is kind of a newer version, the Sahara 2 versus this ERA, and I should be really, really good and look up in the documentation and explain what this other model is, and then when we visualize results from this one, we get these numbers. Now let's compare the two different models. And the reason I think this is, so this is Sahara 2, and here's the big deal. We have energy to grid. I think we can call it this, or the yield, or something like that. And that gives us 2244.01. And, oops, yes, and then we were so proud of ourselves, I thought, 3034. We were so proud of ourselves by matching this result from the hourly data in plane radiation. Okay, and that one was 3034. Now, you could then immediately term this to be the performance ratio. Now, when you think about a performance ratio, I think about things that come up from upstairs, and we do not have to get into whether it's Zeus who causes Jupiter, I guess, who causes the solar, if you're in the Roman times, or whether you believe in any god you want, but this is controlled by something we have zero control over. The amount that actually goes to the grid, the difference between these two, is this 73%. Now this, I think, would be a pretty low ratio. I think it's pretty low, but it's extremely hot, and the total loss, if we put the total loss 1 minus this, it's this 26.6%. And why do I not have the, just a minute? Excuse me. Uh-oh. Okay. I see. Excuse me. Okay. Oh my gosh. Okay. All right. And that 26%, well, they've got 11% for the temperature, spectral effects, and the angle is this one. And then they give you the year-to-year variability. They don't tell you whether it's this or this, but that's very small. And then if we go down to our other model, let's just kind of copy these. Now, okay. And this time we have, oh, 2441.93, a little bit more. This one, it's a whole lot more, 3265.34. And then we have a different performance ratio and a different total loss percent. So if we take especially the total radiation and take this one divided by this one, we get a 7%. We get a 7% difference, which, when you're talking about P90s and P50s and uncertainty, that's certainly not trivial. And I did the same thing a little bit here. This is the grid, and this is the in-plane. Okay, and so we got, this time our performance ratio is this divided by this, and it's bigger. I would expect it to be even bigger. The difference, still 82%, is not that great. And then we do the same thing here. And this time, so that now I get a performance ratio that's different. And that could be related to the temperature effects, although the temperature effects are driven by the temperature, not the irradiation. There could be some other things going on. And the difference, let's take the, okay, so between the models in this case, and we take let's take this one divided by that one minus 1, and we get this time 5.9. So we have a little bit of a problem with the starting point. Now I'm going to pause the video, and I'm going to read in the hour by hour and see if we can match this the same way we matched this. I'm in Copenhagen instead of Saudi, and so we'll have another one saying whatever it was. I'll put it back. I'm going to pause the video now. Okay, so let's continue. Excuse me. Now, for each of these different models of solar power that occurs hour by hour, in the case when we computed the year by year using the SUMIF, I also said, okay, let's compute the standard deviation, and I believe, and well, no, that we always use .s. I don't know why they have .p. The standard deviation, it's a sample. It's by definition a sample because we're using it to project the future. And then we can divide you could call this the coefficient of variation, or you could almost compare it to some sort of volatility. You could almost say, well, if there's a standard deviation of 4.95, 68% of the time will be above one standard deviation or below. Let's just put the NOR normal distribution, and let's take the average plus a standard deviation, and then let's put the average in, and then let's put the standard deviation, and let's make it a cumulative distribution. So we've got 84% percent chance of being at that level or below, and let's compute the, maybe I'll put formula text, okay? Oops, yes, that's the one. And then if we put normal distribution again, and this time take the average minus the standard deviation. Again, I didn't say it one time. This assumes it's a normal distribution, which everybody does because they probably don't know what else to do. Then we have 15% below, and we can confidently say, and I had to do this because I couldn't remember exactly, that this is the probability. Okay. So that we can, okay, 68% is between one standard deviation above and one standard deviation below, and that's how eventually then we'll use that whole idea to get the P90s and P99s and all that, and just give me a few minutes to do that, because before we do that, let's compute the performance ratio and work through this data a little more carefully. The other thing I think maybe it's worth showing you is that if we want year by year and month by month, you know, a lot of you probably use this pivot tables. Okay, like, I just haven't got into them ever. I don't know why, because I'm not really in budgeting and all that. Instead, I would use sum if s, and just you first get, in this case, you first get the solar power, then you compare it to the year, no, I'm sorry, the month. This is the column for the month, which I made, I should have told you, versus the month. The column for the year, and you compare that to the year. And in this way you can get the month by month. You could, if you want, see, well, this is the pattern of a month. We saw that on the other chart, by the way. The reason I'm showing you this is we could also compute the standard deviation across months, and notice that when we compute the standard deviation and then take the percentage of the average to the standard deviation, notice how much higher, bigger it is than this one over here. Okay? But when we go across the year and just sum up the months in the year, okay, and then do the same thing, get the average, which is our famous average, the standard deviation, we get the same thing. And you've got the phenomena that the variation in 1 month is independent. You notice I paused because I made an error. If things are independent, and you can all yell at me about telling me I have no business talking about this, and shut up and everything else, but whatever. Because this really is just kind of fun for me, you take the square of the standard deviation, and then instead of summing the standard deviation, if we summed the standard deviation, we would get this really big number, and the actual standard deviation is much less. And this, after you sum the square of the standard deviation, to add up standard deviations that are independent, and I even wasted time doing a Monte Carlo simulation to prove this, you then take the square root. So you first take this, and maybe how about this? Yeah, let's use our little formula text thing here so we don't forget. So we take the square root, and then when we get down, I take the square, and then when we take the sum, we take the square root of it. and then it gives you magically what seems to be a right answer, suggesting just about any variation in one month is independent from a variation in another month. And perhaps I'm digressing just a little bit, and I apologize for that. Now, the first thing I did was said, okay, well, let's compare Saudi and Copenhagen. Why not? And now we have all of our, through using the lookup, making this little graph, doing it quickly, I put some titles in, and we show our standard deviation. And the standard deviation is a lot lower for Saudi than for Copenhagen across different years. Okay. Here is February, starting on a Monday, 2014. Let's go down to 2013 and see what happens. And we hope it's all okay. And then 2012, because well, the temperature was a little bit different. In this case, we have more than 1,000, our famous 1,000 standard testing condition, where you take a panel and you plop it on you do a test, and and I lost the name of the test. Okay, you do, and then let's put a different a month in here, and I'm trying to make these videos all before I completely lose my mind. And we can kind of see, let's look at a nice, really hot summer month. And what's kind of interesting for me, I think I've already done this a little bit, but in Saudi, that we're not quite at the 1,000. We've got this little more variation now in Copenhagen, except where we had some clouds maybe on this day. We're not there now. A flash test came back to me, the damn thing, oh God. Sorry, I don't mean to cry or moan or shout or anything like this. I'm gonna try to be more professional in my videos after I got in big trouble for being too sarcastic and everything before. So we've got all of our things, and then we can let's look at Copenhagen, and the different models, and this is for me, as a former banker and somebody who's trying to teach some project finance, this is a big deal. The models are giving us different results in terms of standard deviation. Now, you might not think that's very big, and maybe it isn't, but actually it kind of is. And on top of that, they give you, like I showed you before, a different starting point. In fact, let's just review this. So in this video, this very long video that I'm going to make, and I don't care that it's long right now, when we compare the different models, let me see, this is, I couldn't spell Sahara there. One gives you, this is versus Sahara 2. This one is Sahara 2. SARAH2, okay, and we get this in-plane radiation, and this is ERA 5, and we get a lot more. And then we put the old Sahara without Sahara 2, we get less. For Saudi, we had in-plane radiation here. Was this twice as much, but it was certainly a lot more. And then we get 7.6% more. Now, when you're putting, in another video, I'm going to go crazy about mean reversion and non-mean reversion. The fact that this starting point is so different. And then this one is 32, which this is 6% more. This is 7% more. Maybe I should have put it as a percent increase. Sorry about this. And we get different starting points. That is a big deal. Probably a bigger deal, although it's beautiful to make these graphs, of just a period by period variation. And then we can kind of look and see, well, what happened in this day here? Well, everybody agreed it was cloudy and all that, but let's look at Saudi, and here they're all about 1,000. And let me see, this is a little lower than 1,000. This has got some above 1,000, and this one's got below 1,000. So there are certainly differences, and the standard deviation here is really, really low. Okay, which one do you use? And I'm sure that people are wedded to one versus the other, and I'm sure a banker in a wonderful way would say, just think what a banker would say. Come on, think. Tell me now. Take the lowest. Just give me the lowest. And take the highest standard deviation. Let's just mix it all up and do that. I'm not criticizing bankers. They're trying to come up with a downside case, which is really hard. Let's go back maybe to March, and let's try a different year. 2010, March 2nd. Why don't we? I don't know why I'm starting on March 2nd instead of March 1st. Okay, and you can see this has become a really big model now. I'm putting it all on a website. And again, somewhere hovering 1,000. This, we don't even get to 1,000. Look on that scale, and here we don't either. So that's kind of, I suppose, interesting. And then, actually, this is similar. At first I said, look at this. It's the same here, here, and here. It must have been a really cloudy day. But then the next day, this almost got up to 1,000. This only got 400, and this got to 1,000. So we're getting, you have very, very real differences. Now, let's turn to two more subjects. The next subject is going to be the trying to use the some stuff you can find on the internet about how hot a panel gets, and some data from PVGIS to make our own kind of independent estimates of the our own independent estimates of the performance ratio, just so we can understand it. The last thing, I've never run a PVGIS. I have no idea what it is. I know it's from Switzerland, which I like, but I don't know. But we're going to work through it and kind of just try to understand really how these solar panels work with that. So that's the next step, but I'm going to fill in some things and just explain it instead of having you watch me do all the little crap, okay? So let's, to begin this, let's look at a PVGIS run. Now, I used to be all proud of myself for collecting these things, and I looked at these, and there were, no thanks. It seemed that a lot of this stuff was a mystery, okay? And I hope in the next just couple of minutes, we'll be able to kind of work through and understand this, okay? That gives you where you are, the longitude and latitude, and the tracking, some of the same things. We're doing a big difference is you get the meters and the number of trackers, and I'm going to show you that you can do all of this, really all of this, on a per 1,000 STC, standard testing condition, 1,000 watts per meter squared, 25 degrees, not Fahrenheit. And you put in the KWP, which is, it's kind of, this is if you had a single hour for where you had a single hour where you had 1,000 watts per meter squared at 25 degrees, you could get this much power by putting these 30 modules in. We're going to see about the efficiency, and then it gives you the area in meters squared, okay? Which maybe you care a little bit about that. I'm not saying you care nothing. And then they give you the soiling array losses, and then they start giving you these other losses, which, you know, I used to just kind of, my mind would kind of blur a little bit when you looked at this. And some more losses they give you, and they work through some issues with shadings, which are already in the in-plane radiation. So we don't really have to worry about those. And then they give you a performance ratio, 78.73. Remember that one. And they give you the performance ratio by month. And then they give you one of these famous little things where they actually put the soiling loss up here. So the amount of kilowatt hours, I think the soiling loss, frankly, is about the one thing you can control more easily than just about anything else, because you can clean the panels. So just from a philosophical standpoint, I might want to say, let's put that in down here. Maybe we could put it just below there, because I think of the performance ratios, what you cannot control, what comes from upstairs, versus what you can control, like buying panels with a different temperature coefficient. And then they work through all of these losses, and the biggest one, normally, if you're in a hot area, this one is in Nigeria, I think, then you get the biggest kind of loss from the temperature, which the temperature is not completely controllable. Okay, there are some hot days and less hot days, and when we should know that when there's more heat on a panel, it doesn't perform as well. Okay, and then they finally give you this uncertainty analysis, which I have no idea who puts these things in, but it's almost ridiculous. I shouldn't say that, but I'm going to. Okay, shouldn't be mean, you know. So now this is our file, and I hope I'm going to. Okay, I'm going to make sure that. I thought I probably saved the file. Now it's getting to be a very large file. There's another file open, which is part of the series that I'm really trying to work on. And, okay, very good. Okay, at the end of the day, we're going to compute this performance ratio, and we're going to get something very, very similar. And we're going to compute it on an hour-by-hour basis and show you how you can do this. Again, maybe you never, ever want to do it. Maybe the biggest possibility is for a long time ago you've turned off the video. But maybe, if nothing else, you want to just see how it could work. So I took this case for the Saudi Sahara number 2. And the first thing I did is put in the soiling loss. That's okay. Now the temperature coefficient, that's the hardest one. And you look around the internet and you look at Homer, and that's some thing, I think it's not Canadian, I don't know who makes it, but they have some formulas on how you can understand that this temperature is the ambient outside temperature. We, of course, don't care about the temperature when it's nighttime, and we tend to have higher temperature when we have higher solar production. That's not surprising, but here is the problem. The problem is that this temperature is not the temperature on the panels. Now, I looked all around, and I'm proud of myself for finding one little thing where this seems to be nice because it's nice and simple. They took a formula where they take the irradiation and multiply it by 0.03, and they get the temperature difference. Here's the irradiation and this. And I looked all around, and so I tried this one. And so, spoiler alert. I keep on forgetting how to say spoiler alert, but it works, I think. So then we just take the global, this in-plane radiation, and we multiply it by this 0.03. And it gives us the increase in the temperature, not the temperature itself. So look at this. So the temperature here was 19 plus 28. And we add those together. And I hope I'm making these things reasonably transparent. And if you're a modeler, I hope you say, I don't want to just spend all my time with these boring financial models. I want to understand how things really work. So when I think about contracts and when I think about performance ratio adjustments in contracts, and I think about people measuring efficiency, I can start to get it, to understand it. And then, so the next thing you do, there's a temperature coefficient. Oh my God, I can imagine people yelling at me now. And I again looked on the internet. The best one I found was kind of this one that says, and the temperature coefficient, the confusing thing, it's a percent, 0.38%, not 38%, 0.38% per degree centigrade. This temperature, this degree centigrade, is versus 25 degrees. So if you're at 25 degrees, it would be 0. If you're at 26 degrees, the output would go down by 0.38%. So if it was 1,000, it would go down by whatever, 3.8, okay? So I just said, let's take this one, or I looked at some others, and people say, well, for a silicon, it might be about 0.4. Okay, so I just put in 0.4. Now what's really interesting, you can then see if you change this temperature coefficient, the effect on the performance ratio and the effect on the ultimate output of the plant. Now, so I just repeated this because it's such a big deal, and then after that, we put the percent change in radiation, which is just the temperature difference, this difference versus 25 degrees, multiplied by that temperature coefficient. It's easy. And I'm going to put this file right up on the internet, and hopefully you'll say, oh yeah, you can follow it. And then you get the reduction in the amount of radiation. And so in the kind of high hours of radiation, let's maybe look down a couple. Let's find one which is there's one which is 1,000, more than 1,000. You see this one? More than 1,000. We reduce that by 100. And we've also reduced it for the soiling losses. So this 1,000, which is this STC capacity, is never really obtained. I shouldn't say never. You could, if that, maybe if it was, if you somehow had a really cold, really, really sunny day, maybe you could get it, okay? And why does this not go in the middle? Okay, that certainly doesn't matter, you idiot. And so now we have the radiation after that, and we can see, we can go back to that number we looked at, and now our radiation is 800 or almost 900 in this case. Okay, and then what I did is I took some of their other losses, and I just kind of copied this from that PVGIS file. If you want the PVGIS file, you just email me send me an email, and you'll look in chapter 5, and you'll look under resource studies and then solar resource studies. Okay, so here we have some, I think it's better to do it here. We have the soiling loss, and then, by the way, I'll just stop for just a second. They give you the module area, the capacity at STC. You could then compute the capacity per meter squared. This is kW per meter squared, or kWh per meter squared. And at 1,000, when you have 1,000 watts coming down from the sky, you only get 175. That's the efficiency. And if the cost is expressed per this number, well, the only thing that the efficiency really matters, the only thing that matters about the efficiency is how big of an area you need, which could be very important for a rooftop, or it could be influence the amount of operation and maintenance expense you have. So I'm not saying it's unimportant, but that's it. And then I also computed this famous AC to DC ratio, which at first I said, why? This just used to drive me crazy when I first looked at this. And you can answer this now. Why? You have these hours, I'm gonna go back to this one again. You have these hours of 1,000, and you can get all that power. DC to AC is not, it's still electricity. It produces the same amount of electricity. You can have a DC air conditioner even. Why would you take this amount of power that theoretically you could produce and then limit it, and this is this 85%, and we'll get to that in just 1 minute. Just one little minute, because then I put the other losses. And so this, we have some other losses. These are losses before we put in the inverter, and then we get our net amount. And actually, it's very timely, because then I said, okay, well, let's state this AC to DC ratio. Instead of putting all those numbers in and all that, let's just do everything based on 1,000, and it works totally fine. So instead of getting 1,000 of capacity, you get 856. And then they have this little thing, and I always thought, this can't be true. This can't be true. There've got to be some hours here where you're producing more. And we went through a few days, and there are none. And they've got in the loss diagram, they've got this little thing that says where mismatch No, that's a mismatch of the modules and the strings, excuse me. Inverter loss due to power threshold, I guess. That would it be. Okay, that means that we can't use all the power we could use otherwise, and they basically then have total losses from the inverters of 0.85. Okay, not a big number. So let's go back. Again, this I'm going to show you. I've shown you because I'm going backwards and forward in time. And then we get our net production after the inverter. Okay, and okay, and that shows you, oops, that shows you if you do, there are a couple here. There are a few that we lost. Oh, there are a few more. There are a few more. Oh, no. Maybe we should have put a bigger inverter and spend a little more money on this inverter. But that illustrates the issue. Maybe. I don't know. Okay. And they're also apparently reasonable not to do that. And then we put our loss. And then we have the amount of power we produce from this global in-plane radiation, the amount we have after the inverted loss, and finally we have some fans and some times where the thing is unavailable, and it's not unavailable even during the day. You'd like to fix it at night, and there's some external transformer losses maybe that they take away from you, okay? And so the final thing is we have this 2.06 losses, and then that's the amount we sell to the grid. And then you can compute this performance ratio as the ratio of the electricity that goes to the grid divided by the in-plane radiation. And we can take this number for all of the days and then just do our regular old stuff. First of all, we sum it, and we get our performance ratio, and we get our amount we send to the grid. Now, I didn't do this before, but let's compare this. Remember, 2374. And we look at our Sahara 2, and we get a different. That's good. We get a different. We get more power to the grid when we compute it. And we get that 78% performance ratio. Excuse me, here it is. We got 78% performance ratio, which really is kind of fun. Oh God, nothing is fun anymore. But we get this performance ratio here, 78.73 they got. We had 70, where is it? We had 78. Now, if we would put a different temperature coefficient, and if we could really find this stuff, so let's be as optimistic as we can with silicon. Excuse me. This one, let's put minus 0.38, and then put maybe minus 0.49. And this is old. Maybe you get a better performance ratio. Let's say it's gotten better, and I'm sure people will correct me and tell me about that. Let's put 0.35%. And I looked around the internet, and then what happens is I keep pressing F9 to recalculate, and I shouldn't do that. I should do it because F9 is a silly shortcut key they put into this thing. Video, and so we can calculate, recalculate. I hope it recalculated it. No, come on. Just a minute. Okay. Okay. And I might even have to pause. So I put this time I went more extreme even, and I put blah, 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 0.3 temperature coefficient, and the performance ratio goes up. So we can see how that works. And I think what's really important as well, we can start to understand if you're going to, how are you going to do a performance test when the EPC contractor is finished. And you really care not about the final performance ratio, you care about the temperature coefficient, and you put the temperature in, and you put an actual thing here, actual radiation, and you see, and you can put different, the soiling, I don't know what you do, maybe you leave that out because at the test it would be completely clean, and you would see how much you lose, and then you could back into the performance ratio, but it depends on the temperature that's actually hitting the panel. So these are not just trivial things, they really come into play in the contracts and other things. Okay, and I'm going to put this back up to 0.4. Not 0.4, 0.4%. That would really hurt if it was like that. Okay, and that gives us, so we could compute the performance ratio by hour, by month, and do our little analysis on it. And I think maybe it's taking some time to calculate, but I'm just going to continue. These are naturally big files because we've got a lot of data, but it's wonderful to get the detailed data and really present it. So here's our summary with the the in-plane radiation versus the radiation after the performance, and you can see just how it kind of gets capped. And just by making a graph with a lookup, you can do so much. That's one of the really big themes of this, is I was so afraid to do this kind of stuff at first. You're not an engineer, and I doubt many engineers will watch this video, or people who maybe are bankers now and used to be engineers might. Okay, I don't know. Who knows why I said that. Okay, now let's just, this is the uncertainty. Now, in the end, and I assume that I have no idea if these parameters are given by the PVGIS. This 2.5%, which is the year-to-year variability, and now you could almost argue that since debt is repaid on a semi-annual basis, that calculation should take semi-annual periods, but I didn't bother to do that, and I never have. And so this, remember this, we got different values for this standard deviation. Here it's 2% for the in-plane radiation and 1.5% after the performance ratio. I guess because there's a little bit of leveling out if the sunlight is a little bit high, and there'll be higher losses, and you've got a little lower variation. Okay, that's okay. And I had to put this down here. Then they had modeling parameters, whatever that means. This is the uncertainty, and maybe PVGIS, they're from Switzerland, so I like them, maybe my mother was Swiss, okay? Maybe they have done some study of how people make mistakes, and then they've said, what's the standard deviation away around how they make mistakes, and let's make sure it's a normal distribution. So we put everything we've done here is giving us an unbiased average, and then it could go 1% above or 1% below. Of course, when we did the Sahara 2 versus this one, we get a 7.6% difference. That's a lot more than a standard deviation of 1% just by using a different model than a 6.2%. We actually took the lowest one here, so we could try that. So that's the first kind of issue, is where you get the standard deviation, and then the soiling and the mismatch, another 1%, that one's a little bit odd, that says, I think you can control the soiling more than just about anything else because you have a strategy. I don't know about this one. And then this one really drives me crazy, and I've seen people put a lot in here. We are trying to compute the variation around a single year. Degradation happens in the future. And degradation, to say that there's a error in degradation there in your degradation percent is fine, but you're totally mixing kind of concepts completely, I believe, if you put a really big degradation number in there. Now then we get back to the, oh no, unexpected, oh no. Okay, and then we get back to our thing where we sum these, but if you first square them and then sum the squares and take the square root, that's the mean squared error, you get the total variation, which is this 3.1%. And then if you want to get the P50 and P90, you compute 10%, and you take the norm inverse, and you take the average. If I do this, it says take the probability first, then the average, and then the standard deviation. And the standard deviation is this it's not variance, it's standard deviation. Why they call it variance, whatever. This is, maybe they rounded it to 3.1 or something, but I took the 3.1 times the P50, that's the standard deviation. And then we get just about the P90. Okay, it's not exactly, maybe they rounded this to 3.1 or something like this. But this illustrates how you can work through a whole kind of analysis and try to, I think this exercise, hopefully, of just thinking about it yourself is worthwhile. Okay? That's enough.